recording. Now I really double check if the recording starts or not, although I did do that before as well. But it's running. Okay, so welcome everyone. As you may have seen from the email from Shobit, we also had this issue with the posting of the last problem session video. For reasons unbeknown to us, it was very short in the end, 7 seconds, but he went back as I did and then tried to compile the same material from the problem session that he was holding last year. So it should be available to you now. Let me quickly just repeat what I finished with yesterday. The theme that we've been discussing is the relevance of the linearization of a dynamical system to the full nonlinear dynamics. That's why we do the linearization. This is an important subject. And what the sort of the fundamental theorem in this realm is that if you do your linearization near hyperbolic fixed point, and this is the statement of the Hartman-Grobman theorem, which I belatedly but listed. First I forgot, but that's the most important part here. So Hartman-Grobman says that if you do your linearization near a hyperbolic fixed point, and remember the picture that you should remember for a hyperbolic fixed point is this, that it can have eigenvalues, the linearization pretty much anywhere, except on the imaginary axis. And the reason, and why not this line and why not that line and so on. The way to remember this is that you want robust eigenvalue configuration in terms of stability type, not in terms of you don't just want actual stability necessarily, stability type. And the dividing line there is an imaginary axis. So if something is on the imaginary axis, right on the imaginary axis, then it's not going to be robust because under further perturbations, you can move it either to the right or to the left, right? So that's the way to remember. Hyperbolic means robust. Anyway, so if the fixed point is hyperbolic, then the good news is that the linearized system, as we say here, is topologically equivalent to the nonlinear system. So basically you can take the nonlinear system locally in an open set and understand its orbit structure, because that's what topological equivalency is about, just by understanding linear orbit structure. So what's the topological equivalence? Once more, it means the existence of a homeomorphism and continuous mapping with a continuous inverse, which you can think of as a continuous deformation of the orbit structure. And that deformation takes the orbit structure of the linear system into that of the nonlinear system and vice versa. Okay, it's not differentiable. So it's fairly lenient, it's fairly general. And among other things, remember topological equivalence does exist between a stable focus and a stable node. Both are stable, but we think of them as somewhat different in terms of geometry. Once you require a higher level conjugacy, not just C0, then you can immediately differentiate that conjugacy as I did. And then you find that even a C1 conjugacy imposes a very strict relationship, perhaps overly strict, between the two players whose equivalence you want to establish. In particular, the linearizations, the corresponding eigenvalues would have to be exactly the same, right? So this is a weaker notion of that, but what's great about it is that it doesn't come with any additional assumptions. So for hyperbolic fixed points, you always have a basic relevance of the linearization, a basic one, right? If you want more detailed relevance, you say, actually, you know what? I would like to know if the nonlinear system has a focus or a state or a node or a sink, and I'm not content with knowing that it's indeed, I guess, the basic asymptotic stability, say, from linearization, then you need to require a little bit more, and that's what Sternberg's theorem was all about. So basically, you need to require non-resonance conditions among the eigenvalues. I'm repeating this also partly because I made a mistake here. I wrote that this integer vector can be any integer vector, and that's not, I used the wrong notation. I used z, but I should have used the natural numbers. So basically, these are non-zero, sorry, that's not true. Non-negative integers, some of them can be 0, but in total, the norm of this k has to be at least 2, so it's larger than 1, okay? So you can't just have, say, one eigenvalue here times 1, right? Because that would then hit in fact, I shouldn't even, when I don't allow for 1, then I shouldn't exclude this. In that case, this is not important because I'm not allowing for 1. Sorry. See, that trivial relationship, you can always hit an eigenvalue itself by saying 1 times lambda j is, of course, lambda j. That's always the case. But if I require k to be larger than 1 in norm, which means that you can't just have 1 non-zero k, then this is then that exclusion is not necessary. So anyway, if no resonances exist, then in fact more is true, and you can find a CR conjugacy depending on how smooth your original system was. But even C1 would be pretty strong. It means that what you get from the linearization is pretty much locally up to a smooth deformation is what you get from the nonlinear system. But that smooth deformation also cannot be too large because just this statement is then not phrased in terms of the Hartman-Grobman theorem. The Hartman-Grobman theorem thinks of deformations of orbits. Sternberg theorem is a bit stronger also in the sense that it thinks of the right-hand side of a nonlinear system to be reducible to its linearization, okay? So basically, you can change coordinates in a smooth fashion that you preserve the linear part of the system, the right-hand side, and the deformation removes the nonlinear terms, right? So that means that the change of coordinates has to be fundamentally nonlinear because it has to keep the linear part intact. So when you plug in that change of coordinates, in fact, it has to be close to identity to leave the linear part intact. And if it's close to identity plus nonlinear terms, then that means that you can just take whatever that, say, a saddle that's in there, if it satisfies Sternberg's theorem, it does, it always for 2D saddles, we'll talk about that in a second. And whatever you've drawn there, it fundamentally remains correct at the origin, 2 lines running in, but as you move away from the origin, you can start deforming those lines. So that linearizing transformation is not going to take your saddle, say, a system of rotate it dramatically and skew it, but it's also near identity. So basically, you can start with the linear phase portrait, and as you move away from the origin, you have to imagine possible small nonlinear deformations to it, but fundamentally the linear phase portrait under Sternberg's conditions, which is not that much, it's just the non-resonance conditions, remains relevant, and as you move more and more away from the origin, it becomes more and more twisted. And at some point it's going to break down because, for instance, other equilibrium might appear, and that means that your linearizing transformation is no longer valid anymore, because remember, a linear system cannot have 2 isolated equilibria. We talked about that. So your linear system cannot be conjugate topologically to something that has, say, even just 2 equilibria that are isolated from each other. Okay, so I discussed that, and then I'd like to go back to the equilibrium that not the equilibrium, but to the example in which I was just trying to review these concepts so that we're comfortable with them. Is there any question before I go back to the example? The example was about the pendulum. It's a simple example, and I already got started on that. So this was the pendulum example right here. And I just wrote it out in the usual set of coordinates that we use. Mind you that all these results are for first order dynamical systems, right? So when you check their applicability, you have to transform the system to a first order form first, and then check the conditions. You cannot apply directly to a system like this, which they're not in first order form. You need to check the conditions really after you've transformed it to a first order form. So here's the pendulum in the first order form. X1 and X1 is just phi. X2, the velocity is phi dot. I've written that out. The fixed point, the one that I started out with in this example, is the upright equilibrium position. Let's take that one. That's pi for the position, 0 for the velocity. I'd like to understand the nonlinear dynamics near that equilibrium point, and I don't want to use any prior knowledge. I just go blindly. I pretend this is a system that I'm just discovering now. Somebody gave me this model. So I linearize at that point. So I get a linearized dynamics. Y is my deviation from the fixed point. And the way I linearize, obviously, is that, as we have discussed, is that we compute this coefficient matrix of the linearization, which is simply the Jacobian Jacobian of the right-hand side evaluated at the fixed point. When you do that, use the Jacobian as a general point, but then I'm plugging the fixed point. So this comes out to be +1. So this is my Jacobian. The corresponding eigenvalues are +1 and -1. So this is a saddle point. Any saddle point is hyperbolic. There's no eigenvalue here on the imaginary axis, right? This is immediately hyperbolic. So what I'm getting in terms of stability type is what I'll be having, what I'm getting in the linearization in terms of stability type is what I'm going to be having for the nonlinear system, to have a bit more detailed understanding. So therefore, unstable under linearization, so it's going to be unstable for the nonlinear system as well. So the eigenvectors of A, which I just need to draw a local phase portrait, are these when I compute them corresponding to these eigenvalues. And I just wrote out for reference, to be in line with the review we did for linear systems, that once you have the eigenvalues and the eigenvectors, and this is the general solution of the linearized system, which is what you learn in introductory ODE classes, and the more sort of dynamical system-ish way of thinking of this is that you have a linear mapping, which is A to the AT, is the linearized flow map at the fixed point. That's the way it relates to the nonlinear system. Here, F is the full flow map for the nonlinear system, and that acts on initial conditions. So the linear evolution is initial condition acted upon by a linear operator. The nonlinear evolution would be the same initial condition acted on by the full flow map, which is a nonlinear mapping. But the linear evolution can be understood by taking the gradient of the flow map, which is precisely this here. You act on that on the initial condition, but acting on it just amounts to multiplication, because now this is a linear operator. This is sort of the more geometric way of thinking of it. So what's the linearized phase portrait? Mind you also that this is a setting in which we have no resonance among the eigenvalues, because there's no way I can take a positive integer, which is larger than 1, by the way, and I take one of the eigenvalues, so either plus or minus 1, and then obtain either plus or minus 1 when k1 is an integer that's larger than 1, right? So this is never the case. So the Sternberg conditions are satisfied. So we have then, in fact, CR linearization on the right-hand side. So what does that mean in this case? It means that whatever I draw here for a phase portrait will be pretty much the phase portrait of the nonlinear system, infinitesimally close to the origin. But as I move away from it, I will start seeing smooth deformations gradually. So it pays off to draw the phase portrait. That's not too difficult. I take the first eigenvector, so that's -1, 1. So S1 looks something like this. And S2, so this is S1, and S2 is 1, 1. These are supposed to be orthogonal to each other. This is S2. Now along S1, the relevant eigenvalue is -1. So just look at the solution component, whichever way you want to look at it, either this form or that form. When I'm on that S1, that means that this term is 0, so C2 happens to be 0. So I'm just decaying exponentially. Along X2, this term is out because C1 has to be 0. The other way of looking at it is that I place initial conditions either here on this line or on the other line, and on those lines I will have either pure, by this operator, either a pure stretching action or a pure contraction action. How do I know that? Well, because this is how these are constructed. These are eigenvalues, eigenvectors of A, and the the linearization, and the eigenvectors of A are the same as the eigenvectors of e to the AT. So whatever A does along those directions, I don't know whatever A does, but I can take the eigenvalues of A and plug it in here. And it's going to be the action by this operator is either e to the minus ET, which is shrinkage, or e to the minus a to the plus t, which is growth. And the general linear phase portrait is then a linear combination of these, right? And I also know the arrows. So this is what the linear system does. And again, my basis for just drawing these is this relationship, because for a general initial condition where C1 and C2 are simultaneously non-zero, I can just basically take the projection of this initial condition, because this is a linear system, and see what the projection does in this direction and see what the projection does in the other direction, right? And at any point in time, say some time has elapsed for this initial condition, right? So I projected it down initially, and during some time it got here, all right? I also project now in the other direction and run it on that and say it got there, the two, so I can just reconstruct the full evolution by projecting those back up, and wherever these lines intersect, that's going to be my new position. So the evolution of a linear system can be understood by separately looking at the evolutions of its projections onto the eigenspaces, figuring those out, and then once you have considered those individually, you can then sum them up again. This is certainly not true for nonlinear systems, and a lot of people are under the impression that this is doable, but no, it's a very linear property. But for lack of a better tool, a lot of the model reduction that's being done in engineering sciences and applied math goes by this assumption. That's why when you hear about Galerkin projection, various projections onto eigenspaces, they go by this assumption that you can just basically project down to an eigenspace and understand the evolution on that eigenspace and project down the whole equation. And that's a good reduced order model. The reality is that sometimes that might work, and I'll tell you in a second when work means, it's not too bad. In other cases, it can be catastrophically bad. The problem is that you don't know in advance which one is going to be the case when you do this, right? So I'll get back to in a second in terms of, when that works and when it doesn't work. So just to talk about things that arise for linear systems, when you look at a linear system like this, the span of the eigenvectors that are corresponding to stable directions is often called the stable subspace. In this case, in this particular example, the stable subspace is one-dimensional. Okay, but generally speaking, ES is the span of the S, say, I's, okay, the linear spans, such that the real part of the corresponding lambda i's is less than 0. In this case, we only have one of these, so this seems like an overkill, because it's really just that one, the span of the linear space spanned by that vector, but I want to give you a general definition. Okay. Generally speaking, we call those eigenspaces in which you collect all the eigenvectors along which you see decay, and you take that linear span, that's called the stable subspace. Likewise, you can talk about the unstable subspace. Of a linear system. So this is the stable subspace, and this is the unstable subspace, which would be EU. That would be the linear span of eigenvectors for which the real part of lambda j is bigger than 0. Now, for a hyperbolic fixed point, that's all there is, because there aren't any eigenvalues whose real part is 0. I'll just say that in advance, that interesting things happen when you start looking at non-hyperbolic fixed points that have a third type of subspace. It will be called the center subspace, on which the real parts of all eigenvalues are 0. And those are precisely the directions along which you just don't know what's going to happen when you add the nonlinearity. And these are the directions along which interesting things can happen, namely bifurcations, as we say generally, which is basically a change in the phase portrait when you add the nonlinear terms. Those are kind of the sensitive directions, right? But that doesn't, and I'll talk about that more in more detail, because that, you know, opens up a whole area of new things when you talk about non-robust dynamics. Okay, it's non-robust, but after you perturb, it will become robust. But what are the possible outcomes? Okay, and that's the subject of bifurcation theory. So we have stable subspace, unstable subspace, and this is there. Let me actually use that. So this is the notation. This is ES and this is EU. And what turns out already from this, at this level of analysis, that because of the existence of a smooth linearization, which is near identity, let's just try to imagine what happens. So that's sort of a near identity transformation, which leaves the, which takes the nonlinear system, which is x dot equals f of x. In this case, just write that out again, so that we can have it in our eyes, which had the linear part, okay, plus the higher order terms, order x squared. So the ax is the first order term in the Taylor expansion of f of x at the equilibrium point. And I already made a mistake because the coordinate I should be using here, my apologies, is y, the deviation from the equilibrium point. So that's ay, but I can use that y to, I can use the y coordinate for the full nonlinear system, right? Once I have introduced it as a deviation, then I can rewrite the full nonlinear system in those coordinates. I'm sorry, it's getting to be a mess. So this is, then it's going to be f tilde of y, which is nothing else but f x, y is x minus x naught. But I had original x. So x, since y is x minus x naught, x is x naught plus y. I plugged that in there, but then I just renamed it as a function of y. So it starts out like ay, which is the Jacobian at that point, plus high order terms. But the claim is here, from the strengthened version of Hartman-Grobman, is that there's now a further non-trivial change of coordinates. This was just a coordinate shift, a non-trivial change of coordinates, such that if I execute that on this domain, then I can remove this term. So there's a smooth one-to-one, you know, invertible, and with a smooth inverse change of coordinates that actually leaves the linear part untouched. And for that, when you work through that, and you try to perform a coordinate change like that, locally it has to be the identity. And then as you move away, it has to have then order y squared terms. So that means that locally this is the identity asymptotically. So that means that whatever you structure you see here will be unchanged in the nonlinear system. But then gradually you will see departure from that. So for instance, for the stable manifold, the way it will survive in the nonlinear system, there will be a similar thing, is that you will have, as it turns out, although later I will state this as a separate theorem, because right now it's coming out from hand waving in my discussion. I'm trying to give an argument, you know, why this is feasible to expect that this stable subspace has a smooth continuation, which is gradually departing from it, but this is actually a theorem that we will list later on. And this turns out to be called, or generally called, the stable manifold for the nonlinear system. So the stable manifold is defined as the nonlinear continuation of the stable subspace. And it's simply I'm no longer defining it as a span because the world is no longer linear. It's I no longer can capture that with a single direction. But I can say that the stable manifold in the original coordinates is the set of initial conditions in my phase space. And I'm not writing R2 there because I want to give you a definition, or I can write Rn in our case, or n is equal to 2. But it's simply the set of points such that if I apply the flow map to them in the autonomous case, then I find that these initial conditions go to the equilibrium point, say 0, if it's at 0, as t goes to infinity. So it's a bit of a, let me call this x naught tilde. My apologies, because then you might be mixing it up with the original x naught. And then let me call this 0 x naught, because that was the location of the fixed point. So this is the fixed point. In our problem, this was P, and that was in term pi 0. So I'm talking about general initial conditions that have the property that if you flow trajectories from them, meaning that you act on them with the flow map, which means there should be a tilde here, then what you will find is that these converge to your fixed point as t goes to infinity. I already could have given that definition in the linear case as well. So the stable subspace does satisfy that, right? But it was easier for me to describe it in geometric terms because I knew exactly along what direction, unit direction, that would occur. For the linear system, I don't know that. So I can't give you a curve a priori where that happens because that curve is buried in the Sternberg C1 or C2 conjugacy. I don't know what that is, okay? But I can characterize these points by their asymptotic property, which, excuse me, will be the same, which is convergence to the origin. So likewise, there is a nonlinear continuation, which is gradually departing from the unstable subspace. And just to allow for different possibilities, I draw this as something parabolic, right? So which it actually curves back in the same direction. So this one passed from one direction to the other. That's the best I can think of because asymptotically it has to coincide with that curve. But you can have a quadratic tendency like this. And along this, you're going to go away. And this we will call the unstable manifold. Bring it down here. So this is the unstable manifold. Again, this is a nonlinear object. It's a property of the nonlinear system. And the way one can generally define it as a continuation of the corresponding subspace of the same stability type is the set of initial conditions in the phase space. Again, in our case, the phase space is two-dimensional, such that when you act on it with the flow map, then what's going to happen? Well, here things become a little tricky. Why? Because in the linear case, even then, well, I mean, what we would like to perhaps say is that, well, if I act on them with the flow map, let's just look at the linear case, the unstable subspace. Can I get an equivalent definition for the linear case first, just as I did here? One is tempted to say that, well, I act on them on the flow map and they go what? They go to infinity, right? Unfortunately, that doesn't give a unique characterization of that set, even in the linear system, because look at what these linear orbits do. They also go to infinity. So I was able to get away with that in the forward time characterization for the stable manifold, but I'm not able to get away with that for the unstable manifold, even in the linear case. So we have to think of something else. And that something else is, let's reverse time. Because whenever I reverse time, this becomes somebody's stable manifold. So what I require, and that already works in the linear case, just imagine that you reverse time, which means you're running the solutions in backward time, which means changing all the arrows, right? When you reverse all the arrows, then this becomes a unique stable subspace. And initial conditions on this will be running towards the fixed point And no other initial condition will be running towards the fixed point, only these. So I'll follow that recipe for the nonlinear case as well. So these also converge to x naught, but now as t goes to minus infinity. And this is important, that it's minus infinity. So these turn out to generally exist, and we'll have a theorem for these before I go to bifurcations. But I just wanted to tell you that based on the Sternberg linearization result, you can already anticipate their presence. And it will also be a theorem, as I show here, that the nonlinear continuations, the stable and unstable manifolds, are in fact tangent to the linear counterpart. Okay, that's going to be part of the theorem. But here I give you a reason why you actually expect that based on what we already know, because asymptotically, they have to coincide, right? So there's this gradual departure. And then when you try to piece together what you might have, you know, for the nonlinear trajectories, let's try to pick a color which I have all sorts of colors here now. I have the stable subspace. So what's a good color? Now that's a tough choice, right? So I don't know, let's pick this one. So now my two guiding posts are this curve and that curve. And fundamentally, I should think of as saddle type dynamics, right? Because the nonlinear dynamics is a smooth deformation of the linear dynamics. So I didn't just do by best and fill in the remaining spots. Perhaps I beef up these lines a little bit so that ultimately I get a saddle looking thing, but it's deformed. The more I move away from the origin, the more it's deformed. But fundamentally, if it is of saddle type, because I have Hartman-Grobman still, that tells me that it's just a twist on the dynamics, orientation preserved, right? And it's invertible. So this would be the nonlinear dynamics. And let me also strengthen these curves a little bit. And then I go back to red here. So these are the arrows there, and these are the arrows there. Okay, and now let me get back to the point that I said that, well, a lot of applied science does nothing else when I mean, you know, in everybody's defense, high-dimensional dynamical systems are exceedingly difficult to compute. And one just has, you know, when you have millions of degrees of freedom and you have to run several simulations and your right-hand side is not even explicitly defined, but you have to call the routines even to evaluate those, then this is an immense task. And then you might ask, why don't you throw more processors at it? Because we just have super fast processors. But it turns out at over a certain limit, and you reach that limit actually pretty soon, adding more processors makes things worse, because there's going to be cross communication among processors and everything, and that slows you down. So amazingly, some of the finite element codes that people complain are taking too long are being run on 4, 5, 6 processors because you throw more at them, then your cost goes up, right? So that these have been optimized, right? So something has to give. It's not about having more powerful processors, but not at the current scale, at least, of speeds. And then people then naturally talk about model reduction, which is a very big area right now. And what everybody's go-to solution first is just modes. You know, pick modes of the linear system, project the nonlinear system down to it, and just let's hope for the best. And you kind of see when in this little example, when that works and when that doesn't work, right? So if I'm in a domain that, say, by the way, if this is a bona fide nonlinear object, if you had a way of reducing your dynamics to this one, that it's questionable whether that would be relevant, but it would be exact, because you start on it, you stay on it. So what would be a good relevant model reduction target if you want to reduce your saddle dynamics? Suppose this is a high dimensional system. I submit to you that it's the green curve, although it's the unstable manifold, and it might send the message, oh, unstable, I don't want anything unstable. It's unstable because of its internal dynamics, but as far as its role in the overall system dynamics, it attracts everybody else, okay? So if you want actually a good model, which is valid for a while until you leave from the origin, then this should be the curve that you're after. If instead you project your system into an eigenspace, you see what happens. That's not an invariant curve for the nonlinear system. So formally, you're projecting your equation, and since you have projected it, you're moving on it, but the real nonlinear system is not moving along this line. The real nonlinear system is departing from that. Now, if you're lucky, because the shape of this curve, the curvature is such that it's the way I'm showing it now, as opposed to say this, which could also be the case, right? Then that approximation projection to the linear system, when this happens, is really bad. But if the curvature of your relevant invariant manifold, as we call these, invariant because you start on it, you stay on it, is large, is small, sorry, you're close to it, then you're lucky. Unfortunately, you really don't know this going into the problem. So that's why in some cases it will work, in other cases it will not work, right? So that's why you always have to check. And the way, when it doesn't work, then people basically start adding more and more modes, which becomes uneconomical because, in fact, you could get away with a one-dimensional model if you invested a little bit in understanding the nonlinearity in the system, rather than starting adding 10 modes, 20 modes, and so on. Not even mentioning the fact that if you're adding 20 linear modes, that's still just a subspace and it's still not invariant, right? It's just that you're just throwing everything you have at it, and you just hope that with those additional directions, you're getting close to the true nonlinear curved structure, right? So this is just a, and I think I'll have more time in part 2 of this course to actually tell you how one can do that better and really go after the nonlinear structures that are targets for model reduction, rather than keep throwing modes and increasing the dimension of the reduced model unnecessarily, because in fact here you would have a perfectly valid one-dimensional reduced order model, at least while you're in this domain. Okay. All right, so that's just a bit of philosophy on top of the pendulum equation. So what Hartman-Grobman would only tell you that these are C0 curves, because that's the realm of Hartman-Grobman, continuous deformations. But in fact, Sternberg tells you that these are nice, smooth curves. So I will just say that existence and smoothness of the stable manifold and the unstable manifold follow from Sternberg's theorem. Okay, so that was sort of the local relationship. That this is how far I can get without doing any work on the nonlinear system, just linearization and having the right theorems about the nonlinear behavior at hand. Okay, at least for the saddle point. Now, does this system have other equilibria? Yes. So this is 2. We know that physically to expect another one, which is the lower equilibrium position, right? Formally, when you go to the equations of motion, that means you plug in x1 equals 0 and x2 equals 0. And that's also a solution. So the fixed point at q equals 0, 0. So that's the second question. Again, I'll find that just from root finding, if not by hand. But again, if I want to go by the book, then I linearize my dynamical system there. And again, I get a linearized system of the form y dot equals ay. In this case, y is just x because the fixed point from which I deviate is at 0. And a is just, again, the Jacobian of the right-hand side taken now at 0. And if you look at that Jacobian, 0, 1, minus 1, 0, because if I scroll back, This was a general expression for the Jacobian here, right? This was general. But earlier I plugged in pi 0. Now I'm plugging in 0, 0. So when I plug in 0 here, then the cosine of 0 is 1. So this is going to be minus 1. This is how I got that. So again, I can solve the characteristic equation of A. So I get two eigenvalues now, which is lambda 1, 2 equals plus minus I. So at that point, if this is all I know about the system, I should be saying, wait a second, this is not a clear-cut case because the fixed point is not hyperbolic. And whereas with the pendulum, we are pretty comfortable and we know what the outcome is ultimately, you're not learning all this to repeat the modeling of the pendulum or your life again, but you're learning to be prepared for models that you're deriving or other people are giving to you that are high dimensional, and you have no idea what they're producing, right? Or in fact, it's a structure to be designed, and it's up to you to make sure that it produces the right behavior. Okay, and we'll see if all goes well, we'll get to an example soon. So it's not hyperbolic. So what you get is not automatically carrying over to the nonlinear system unless you make further assumptions. So what is it that you get? So first of all, let's just fix this conclusion, is that the linearized dynamics is a priori, which means in this case, in the absence of further considerations, a priori, what did I say, inconclusive. For the full nonlinear dynamics. So what do I get from the linear analysis? Well, I have a saddle point, not a saddle that I had at the other fixed point. So these are the two coordinates, y1 and y2. I know I have a fixed point here. And it's also reassuring to know one thing, that when I add the nonlinear terms as perturbations, which are naturally small close to the origin, because when x is small, then anything over the order of x squared is much smaller than the order of x, right? So to kind of work that out, if you have the original, if you have a system like this, x dot equals ax, which is the linear part, okay, plus, let's just call it, you know, g of x, and g of x is of order x squared, which is the partition. And let me move this a little bit. Move this away a little bit before I draw anything, because I want to argue that the nonlinear system is always a small perturbation close to the origin, in the sense that we have discussed, even with an epsilon, which is, I have no epsilon here, right? So how can I claim that? So the way I can claim that is that, sorry, I'll just put that here. So, you know what, I just say, you know, let's focus on a vicinity of the origin. So let's actually introduce a new variable, and that new variable will be, say, z, and I define it to be epsilon, x to be epsilon times z. So when this new variable z makes an order 1 variation, you know, unconstrained, at the same time, that will translate to an order epsilon variation to x. It's just a rescaling. This is just rescaling near the origin. And I say near the origin because I think of epsilon as always in math, it cannot be negative. It can be 0, cannot be negative, much less than 1. Now, if I then, in the new variables, I try to figure out the dynamics, then when I take x dot, then using this, so I'm working out the equation in the new variables, the x dot will be epsilon times z dot, right? And ax will be a times epsilon times z. And then I have, this looks like plus minus, but it shouldn't be. Plus, I have g times what? So epsilon z, sorry. Okay. But then remember what g was. So I start rewriting this plus. So g was order epsilon squared. So when I plug in epsilon z for x, then I get z squared, but I also get epsilon squared that I can pull out for some g. You know what? I'll just write order epsilon squared. It's good enough. Okay. And then look at the equation that I have now for z. It starts out like this, and this is the form of what I was getting. So this means that I get z dot equals az plus order epsilon. So in these scaled coordinates, the nonlinear system is always an arbitrarily small perturbation of the linear system. That this was the small perturbation setting that we were looking at, right? And in this setting, we have shown that if you really have a controllably small perturbation, and you do have that here, it's up to you how close you want to go to the origin. If you keep epsilon really small, it means you're very close. Not so small, large, but it's up to you. It's just your area of focus, right? So you can make it arbitrarily small, non-zero still. Then we are in the small perturbation setting in which we concluded that even though this equilibrium point is not hyperbolic, as long as none of the eigenvalues of A are actually zero, spot on, the equilibrium point will persist. And this is one of those cases because the eigenvalues have non-zero imaginary parts, so they're non-zero. So that's not a question that the equilibrium point will persist. You could say, I knew that. I mean, look, I know that anyway, because I know what the full pendulum does for it. This is an equilibrium point. And you're right. That's extra information that you have here, right? But what if you start introducing imbalances into the pendulum slightly so that its equilibrium point is actually not at zero anymore, or asymmetries? It's good to know that as long as your modifications to those pendulum are small, there will be a unique nearby equilibrium which scales in order with the amount of modification that you carried out, right? So that's the advantage here. So in this, let me just write it out. This is a small perturbation setting close to the origin. So the fixed point survives. For small epsilon, even though non-hyperbolic. Now comes the special information about the pendulum that, you know what, I can go and look at the, you know, I'm looking at the full equation when I do this analysis, and I know that the full equation, the full nonlinear equation has this as a fixed point at x equals 0. So not only does it survive, in this case, it doesn't even move when I pass from the linear to the nonlinear system. Okay, that's fine, because that is one particular, you know, nature of this type of a small perturbation, that I still had z there in here, and this was vanishing when the argument was vanishing in there, gz. That's what it means to be order s squared. So this will also vanish. All I did just rescaled. But more generally, when you have a center type fixed point like this one, it may move when you add small perturbations to the system. So it's a center type fixed point. So the orbits will be closed, but understand that this is for the linear dynamics. Now, we've already discussed the pendulum, and it turns out that these also, you have a very similar orbit structure for the pendulum, even in the nonlinear case, but that's by no means given in general. The reason why we have that is that the pendulum happens to be a conservative system. And we know that at all orders, energy is conserved, so you have to be moving with energy level surfaces. You can, however, have a version of the pendulum, say with viscoelastic damping, which is nonlinear, and the linearization would know nothing about it. It would still predict a center, but when you add the nonlinear term, it would destroy these closed orbits and you would be spiraling into the origin, okay? And that would be the result of the fact that this is a non-hyperbolic fixed point. So, so let me just write some of this down. So in this case, conservation of energy causes the centers to survive in this 2D system. I have to say that even this statement is even not true when you have a 4D system. Even if it's conservative, what you get from the linearization is not generally what you get for the non-linearization, even though it's conservative. If the equilibrium point is non-hyperbolic, you can in fact get arbitrarily close chaotic dynamics, which you definitely don't get from the linearization, right? So this is really specific to 2D and really conservation of energy. Generally speaking, all bets are off. But I want to tell you that if you give up conservation of energy, even then, you no longer have the safety of claiming that what you see in the linearization is what you get for the nonlinear system, okay? So if we add, say, nonlinear damping, which, you know, all systems are damped in practice, and suppose this is your model. So suppose your pendulum equation was something like this, again, still non-dimensionalized, phi double dot plus, and now I'm going to add the damping term. I think I just picked, for argument's sake, if it was simply viscous linear damping, then it would already show up in my linear analysis, and it would have changed my conclusions. I would not be getting this linear phase portrait. But let's assume it's really nonlinear. So let's just say it's phi squared, phi dot, sine phi. I think that's what I picked. So again, if x is phi dot, fixed point you still have. No change in that conclusion. And the linearization is still this. Why? Because this was a nonlinear term that vanishes at the origin, so it will never enter the linearization. When I take the Jacobian of this term, which would be, you know, something like x1 squared x2, I take one derivative of that with respect to any variable, and I evaluate it at 0, that's still 0. So it has no impact on my linearization. My linearization, again, returns this phase space structure. So I would say, okay, wait a second, I'm used to the fact, you know, this is mathematical mumbo jumbo, but, you know, it works out usually. The bad news is it wouldn't work out because this is now damping that takes away your energy. So there's no way you can return to the same orbit. So in fact, if you work out the d by dt of the energy, and just leave that to your long trajectories, energy depends on position. you can do the same energy estimate I did before, right? You know, multiply this by phi dot, rewrite. I mean, what you will be getting is something like this when you pass to x coordinates, is x1 squared, x2 squared, if I did it correctly. And that means that unless you're at x1 and x2 equals 0, or unless you're at a point where one of them vanishes instantaneously, the energy keeps decreasing. And in the phase space, since x1 and this is the same one as x1 and this one is same as x2, those points are here and there along an orbit. So instantaneously, your energy is not going to grow back, but at least you're not losing energy when you're hitting this point. But the minute you're leaving that point with finite velocity, you're already losing energy. So you're actually diverting from that orbit. Now, again, here, instantaneously, you're not losing energy, but the minute you're leaving that point, again, you're losing energy. Again, instantaneously not, but then again, yeah. So this is what transpires in the end. So that will be the nonlinear dynamics, which is by no means topologically conjugate to the linear dynamics. Now, this will not happen with the saddle point, because the saddle point, even if you add this type of nonlinear damping, again, the linearization will not know about it, but we have a guarantee from already Hartman-Grobman, but also Sternberg, that in the case of the saddle point, yes, that nonlinearity might introduce some additional deformation here, you know, but fundamentally it's the same phase portrait. And that's the significance of hyperbolicity. So this turns the linearized center into a nonlinear stable focus. And you could say, all right, that's no big deal. I mean, still, all right, the linearization predicts that I'm stable, the Lyapunov stable. The nonlinearization makes it even better that the nonlinear system is asymptotically stable. I, in fact, gained by this, right? I was being even conservative that I'm only neutrally stable, and in fact, I'm asymptotically stable. Is that a big problem? The big problem is that you will never know that in advance, because I might just go back and change this sign to negative, which means, say, coming from a control force or a negative damping, and then it will do the opposite. So you're getting the Lyapunov stability from linearization, and the nonlinearity will then completely destabilize your system into an unstable focus. And that's something you don't want to know. You do want to know about, except you will not know in advance if you only focus on the linearization. So then if we have, we can just say negative damping, which you can just think of as forcing, nonlinear forcing, or a control force. So you look at the equation phi double dot minus phi squared, phi dot minus sine phi. Again, the linearization will know nothing about it, but it will ultimately cause this to happen, instability. Instability in the nonlinear system. That's why in the absence of, say, a conservation law or something, it's very dangerous to draw conclusions about dynamics near non-hyperbolic equilibria, okay? So that's why if it's hyperbolic, if it had been a damped focus, all right, to begin with, because I had linear damping here already, then you would be fine. Or at the saddle point. But when you're neutrally stable, it can go either way when you add a general nonlinearity. Any questions? I have a further example in the notes that drives this point home. It's a one-dimensional example. It just shows that is example 10. It just shows that you don't even have to go to 2 dimensions to see this, all right? You can have a one-dimensional dynamical system, and if it's linearization, maybe I just mentioned that, is non-hyperbolic. I'm just not going to go into all detail because I think I've done that in this example. I'm just going to mention that this is not because I picked 2 dimensions. So generally speaking, hyperbolicity is essential for the topological equivalence, or in other words, for the relevance of linearization, topological equivalence between the linearization and the full system. And really, you don't have to go far for examples. X dot equals ax cubed, right? And it's just, so x is one dimensional. And let's just say a is bigger than 1. And then the linearization, let's say x equals 0, which is clearly a fixed point. So on the one hand, linearize at x equals 0, then, well, take the Jacobian of the right-hand side, that's ax squared, plug in x, that's identically 0. So your linearized dynamics is y dot is equal to 0. That's your linearized dynamics, because the Jacobian derivative is identically 0. So the phase portrait for this one-dimensional linearized system is quite boring. It's full of fixed points. This is the linearized dynamics. Whereas if you look at the full nonlinear system, we've done that. We have tools to understand fully this one-dimensional nonlinear system. Remember the little game that if I call this, that's the right-hand side, then all I need to do is just to understand immediately the global phase portrait of this system is that I just need to graph f of x as a function of x, right? And in that case, there's no reason for me to stop here, okay? If a is, say, bigger than 0, which I have assumed here, and this is just a cubic polynomial, cubic parabola. And the right-hand side is then something like this. And why did we graph the right-hand side? Because we figured that whenever it's positive, I'm going to be growing, and whenever it's negative, I'll be decreasing. This is one-dimensional dynamics. So I have 0 here, and away from that, all trajectories just grow. And below that, in the other side, all trajectories decrease. Okay. So you're not going to find any open neighborhood in which there is no open neighborhood of this phase portrait, which would be topologically equivalent to this phase portrait. Because remember, that would, and topological equivalence is the weakest form of equivalence, because that would imply that you have a continuous mapping with a continuous inverse that maps orbits to orbits. And it has to be one-to-one, right? Now here you have infinitely many fixed points, here you just have one. So that would mean that, okay, one of these fixed points is mapped into one of these fixed points, but then the other orbits would have to be mapped into other orbits, and the homeomorphism cannot map an orbit like this, which is open from one side and infinitely long in the other side, into a point. So there's definitely no correspondence between the two, okay? So I'll just quickly say no homeomorphism. So what you have here is the nonlinear dynamics. And we see all orbits, right? So this is the nonlinear dynamics here on the one-dimensional phase space. So no homeomorphism. Between I'll just say that the two sets of orbits. Because unavoidably it would mean that you take, I exclude a point, but this is a trajectory, you know, that cannot be taken by age into a point. And why point? Because that's all you have here. You only have point trajectories. So that cannot happen. So totally irrelevant. And even in terms of stability, right? Because you could say, all right, but you know, this is giving me an idea that things are bounded. Nevertheless, I'm stable. No, you're unstable in reality, right? That's why you have to be careful. But you don't have to go to the pendulum to see that that was the point of this example already in one dimensions. You see that. Now, we therefore very much like hyperbolic fixed points, but from an engineering and design perspective, just because something is hyperbolic, it doesn't mean that it's desirable, right? Let's just take the or that's our final answer to any question. Let's just take the upright equilibrium position of the pendulum. That's an unstable position. And suppose it's up to you to design a structure which is comfortable to have this position as its operating position, because small perturbations in the absence of damping, say, just bring it back to it or control. This is clearly not. Although clearly, I mean, in robotics, there's a lot of effort going into developing robots that can stabilize this. That's called balancing, right? So it's a nice challenge, obviously, but for most practical applications, you want, say, stable positions. So you have to have a way of also establishing beyond hyperbolicity the actual stability type. But if your only tool is linearization, which is always our first tool, that requires a good understanding of the eigenvalues of the linearization. And of course, unless the Jacobian of the linearization is huge, and we're talking about millions of degrees of freedom, the eigenvalue calculation is not really a challenge. Even if it's millions, you can get them fairly soon, but they will be inaccurate, okay? So in the realm of low dimensions, calculating eigenvalues numerically is not a big problem. So you might ask, why don't we just skip and go on to other things? And I would say, yes, if you have a specific A, then MATLAB or any code that you use will return the eigenvalues. I give you another A, return the eigenvalues. And suppose I want to discover the system for a lot of over a whole parameter space. Then what do I learn from this exercise, right? And then it starts becoming costly, because maybe I have 52 parameters in the system, and so you have a 52-dimensional parameter space, and each and every point of the parameter space I'm asking for the eigenvalues, right? And even then, then we have to contend with numerical errors and so on. In other words, wouldn't it be nice to have a tool which is still kind of analytic, that decides about the main question? Is this equilibrium not just stable, but asymptotically stable? Because again, for practical relevance, we want oscillations that settle down, or not? Can I perhaps have a tool that basically just based on A, without having to solve these really high dimensional characteristic equations, which is a pain, right? Can I say something based on that? The answer is yes. So there's a classic result that I wanted to just cover. I can state the results and maybe do an example next time. So this is about determining asymptotic stability, sort of in what you could say analytic way. So determining asymptotic stability from linearization. And especially this becomes very useful when you have to design a structure, and engineers like basically, you know what, I have to stay in this domain on the parameter space, or in that domain, or because design is always a multi-parameter optimization. Okay, so you also have other things to worry about. So it's good to have a ballpark that as long as I stay here, then I can move around my design parameter point and still be asymptotically stable, but simultaneously I can also satisfy other conditions. So this is essentially a linear discussion, because I have a linearized dynamical system that I have obtained, and Y is n-dimensional. Accordingly, this matrix is m by n. Okay, and I just remind you that A does come from a linearization of a nonlinear system, which I have carried out at a fixed point x naught. So that would be the fixed point of the underlying dynamical system x dot equals f of x. Okay, so that means that at that point the right-hand side vanishes. The question I wanna worry about here, well, first the setting is that assume excuse me, assume that the real parts of all eigenvalues are less than 0. So these are the eigenvalues of A. So we know that A, we have a hyperbolic fixed point because none of them are on the imaginary axis. So what I'm getting is robust. And I like to, no, sorry, did I? No, I mean, it's this circular argument. If I know this, then I know everything, right? Sorry, not assume. Would like. Sorry about that. So I would like to establish asymptotic stability, but not in the brute force way of having to fix A, which might be, 50, 100, or 200,000 dimensional. Clearly, I can't do symbolic calculations of eigenvalues. Let's just review, right? That I certainly have I can solve the characteristic equation when it's quadratic, so it's two-dimensional. I have Cardinal's formulas, which tend to be complicated, but still they give you complicated results. And but that you can solve in principle a three-dimensional polynomial and for roots. And we have the fundamental theorem that below over 5, degree 5, there's no general solution formula for polynomials. So you absolutely have to do it numerically when n is at least 5. But even if it's 3, if you ever worked with Cardano's formulas, yeah, you have to make substitutions, you get cubic roots and whatnot. They're not very insightful. You're interested not necessarily the eigenvalues, that's the thing, but your interest is whether they have real parts that are negative or positive. So can we actually just cut to the chase and have a criterion that tells me that the eigenvalues have a negative real part without me having to calculate the eigenvalues, right? Because ultimately that's what one cares about at first order, at least. So the question would be, criterion for the above without calculating lambda I numerically, which, unless m is less than or equal to 3, that's your choice. That's your only choice. And again, then you have to, generally speaking, this depends on parameters. So that means you have to fix your parameters. Now, this was actually a big achievement in dynamical systems, and it has there's a sufficient and necessary criterion, it turns out, for this to be the case. And it goes by the name of Routh and Hurwitz, or Hurwitz eigentlich. So Routh-Hurwitz, and this Hurwitz was actually Adolf Hurwitz, who, as I understand, was a professor here at ETH, the math department. I mean, I think this was in the, oh boy, I don't have the, it's late 1800s, I think. So I'll just say it was actually Professor Adolf and ETH. Although at the time it wasn't, I still had a different name, right? As I remember. So he had big shoes to fill because I think I read somewhere that he was hired to replace Frobenius, who's also a huge name in say integrable dynamical systems. So ETH traditionally has been very strong in these. And Hurwitz was, in fact, this wasn't his area. I think he was working on largely on algebraic problems, because ultimately this is an algebraic problem. You can very quickly calculate the characteristic equation of a matrix, right? Because that only involves multiplications and additions. You can automate that very quickly. And you don't have to have specific numbers in the matrix. You can have symbols in the matrix, and in a split second, you can write out, when you have a computer, the characteristic equation just symbolically. So then it becomes an algebraic problem. Under what conditions on these coefficients of the polynomial can you guarantee that the roots of the polynomial have negative real parts? It's a purely algebraic problem. So but to somebody who just works on polynomials and algebraic problems, this seems like, why would I care whether the real part is less than 0 or bigger than 0? I mean, why would I? There's so many other things I can ask, right? So you need somebody who's applied and says, no, this is really important. This is really important. So he needed somebody who said that this was really important and brought his attention to this problem. And that's another ETH professor who was in my department. And that was Aurel Stodola, there's a prize named after him. Our department gives that out every year to a very distinguished person in any area of mechanics. And that was just the other day, that prize lecture. This year, the winner was Detlef Lohse, an incredibly big name in fluid mechanics. So he was giving a lecture, nothing related to this, but the professor, every year we give out that prize. The department had always talks about Stodola, who was a professor here, mechanical engineering, and his main expertise was, in fact, he wrote the first textbooks on turbines. And to him, it was gas turbines, notably, I think. And to him, the stability of turbines was of utmost importance. So he knew very well that linear stability analysis is very important. But since he was building more and more complicated models, he wanted to have this tool that, hey, based on just can I design turbines, and can I just, generally speaking, design mechanical structures by having a good region in the parameter space, whatever the dimension of the parameter space is, so that I can only move in there, because if I move out of there, I lose stability. But can you just give me a tool that for quick assessment, for design? So this has a very important practical motivation, right? And then he went and talked to his colleague at the math department. So I'll just mention that. So that's DMAFT at the time. So that was a mechanical engineering professor. This is how ETH is related to this. This is not how, because I know about it. I mean, it's a very well-known criterion. Only later, I learned this already, I think, as not an undergraduate, but maybe, as a master's student. And I didn't know all these connections, but then later on, when I landed here, then I realized how ETH was involved in this. And the criterion is really, really simple. So we now transform this to an algebraic problem. So we talk about the characteristic equation, but in fact, slightly more general, because when you write out the characteristic equation, the leading order coefficients, see, you're talking about determinant of A minus lambda I equals 0. So the leading order coefficient, then, if you follow this formula, then tends to be 1, but this is for more general polynomials. Maybe you wrote it out in a way that you didn't normalize the leading order coefficient. So you have an an here, and then you have an minus 1 lambda n minus 1, and the powers are going down. And you finally have a1 lambda first power plus a naught bigger than 0. So this is the characteristic equation. equals 0. Okay. And then assume, just one assumption here, that you set it up in a way that A0 is positive. Now, if not, multiply by -1. Well, and then you say, okay, but what if A0 is 0? Then that doesn't make any difference if I multiply by -1. I'm never going to satisfy this assumption. This might be a very strict assumption. Well, I submit to you that if A0 is 0, then you're done. Because if A0 is 0, so this term is out, then look at what you have contains lambda at least at first power. So you can factor out lambda. So lambda equals 0 is a root, which means that no matter how you would love to have it, the real part of lambda, there will be an eigenvalue whose real part is 0. In fact, the eigenvalue is 0, so you cannot have asymptotic stability from linearization. So you wouldn't even then bother, right? If you have set up a model for which no matter what the parameters are, so no matter how these coefficients change, you universally have A0 equals 0, then no matter what you do, you're never asymptotically stable. So that means you have to revisit your whole model before you do this analysis, okay? So I'll just say that note, if A0, so here I have to be a little bit more precise and not if not, that if A0 is less than 0, okay, then multiply by -1, and then you're okay. Multiply the whole polynomial by -1, right? That's what I mean. So if A1 is 0, then lambda equals 0 is a rule. You have no asymptotic stability from linearization, not a chance. And generally speaking, I don't recommend that you rely on the nonlinearity either, because the equilibrium point is non-hyperbolic. So your unmodeled effects can have major impact on the linear dynamics. So you want to rethink the whole model anyway. Okay. So if that is it, so you can always achieve that in realistic cases when A0, you can make A0 positive. If it's negative, just multiply everything by -1. Okay. And then in order to state the results, I only need to introduce a sequence of numbers. So define a sequence of numbers as follows. So D0, capital D, will just be A0. So simply I take the first member of that sequence to be A0. And the second member of that sequence will not be much different. I take capital D1 to be A1. So far, I'm taking these coefficients. But then instead of taking A2 and A3, I start defining these as appropriate determinants. So D2 will be defined as a determinant that the way I try to memorize this always is that I use the coefficients up to that order, except for A0, excuse me, and I write them in the diagonal of a matrix. Okay. So for D2, I need the 2 that are not equal to A0. I write them here. And then in the diagonal, and then to the left and to the right, I start filling up these slots with lower order coefficients. So here I will write A0, so I'm going downwards. And then here I go upwards, so I write A3, and I take the determinant of these. So at least this is the way I try to memorize, and even then I tend to forget, but this is one way to sort of reconstruct this. So when you go for D3, just to practice the principle, I take E1, A1, A2, A3, And when I go to the right, I start listing the coefficients until I run out of them. If I run out of them, I just write 0. Again, to the right, I write the lower order coefficients. To the left, I write the higher order coefficients until I run out of coefficients, and at which point I just write 0. Okay, so how would that work here? I start by writing A0 here, but then I'm out of coefficients. So the next one I write is 0. Likewise, I start from A2. I write the lower order coefficient here, no problem with that. And I write a higher order coefficient there. And for A3, I write A4 here. If my polynomial was in fact, just cubic to begin with, then this would actually be 0. And that is because, you can always write 0 times lambda n plus 1 here, and that would be your next formula, your next coefficient. So that's understood that some of these might be 0 because when I go, well, in this direction, I will always run out of numbers at some point because A0 is the lowest one. So I start writing zeros. And then in this direction, when I run out of them, I formally, this definition just means I write zeros for those, right? And then perhaps you get the idea, but what I tend to do is just sort of highlight this, that this is the part that I try to memorize. And this is how you then go for higher order terms. So dot, 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 up to dn, which is the order of your polynomial, right? And again, that's the rule would be is that you start with A1, and in the diagonal, you write up to AN. At that point, you're surely not having any higher order coefficients, so it's all zeros here. Here you have A0, and after that, it's all zeros. And then you fill up the rest accordingly. But the rule is, again, that you first lay down the diagonal. To the left, always to the right, always lower order ones until you run out of them. And to the right, always, to the left, sorry, always higher order ones until you run out of them. And in the last row, since you started with the highest order coefficient, you're sure to run out of them already in the first step. There's no more in your polynomial. That's your highest. So you just keep writing zeros here. Okay. And you do this, then therefore you have a sequence of these dn's starting from 0 to n. Okay. And then the result is actually very simple. So what I'm going for is I'd like to secure that the real parts of lambda I are all of them negative. So I want to have this for all I going from 1 to n. I always have n roots, but the fundamental theorem of algebra, some may be repeated, some real, some complex. But the real part of the real ones is always well defined as well. So this is fully equivalent to the requirement that the di's are positive, strictly positive, from I equals 1 to n. So to appreciate this, this can be fully done symbolically, right? You can compute these determinants in a split second, just by in low dimensional cases, even by hand. But even now, use a symbolic package, you can have a matrix full of parameters and just ask the package to write out the characteristic equation. It will do that for you. Some of these AIs can be, lengthy numbers, and then arrange them in these determinants. And at the end of the day, you will get n expressions. It's fully symbolic. So all your parameters are in there. And you can then ascertain that the equilibrium point is asymptotically stable if all those are positive. So basically, in a parameter space, each defines a surface, generally speaking, generically speaking, and then you plot all those surfaces, and together they will demarcate an open region of the parameter space, generally speaking, in which you have asymptotic stability. So you know that you can place your design there. If you're there, and then you can start moving around to satisfy other conditions within that domain. There may be multiple domains, in fact. And you also, the only thing, this doesn't give you the eigenvalues, but the only thing you can sort of guessed already that as you start moving closer and closer to the boundary of these domains, then those real parts actually start moving closer and closer to zero, right? Because right there, you're violating the condition. So from that, you can guess that the closer you are to the boundary of this domain, the weaker your decays will be. So if you are also going for, you want quick settlement to your equilibrium point, you'd better be away from the boundaries, okay, as much as you can. Okay, but this gives you a ballpark already. And then also, just one last remark. This is the statement that there's also already a necessary condition that you can by inspection almost in most cases. So this is not sufficient, but necessary condition. So that you can use to exclude the possibility of asymptotic stability. If it's violated, it's simply this. So in other words, you write out a characteristic equation and your main concern is stability. And from the physical meaning of those parameters in the mechanical system, you know that, oh, this one is for sure negative, cannot be asymptotically stable. Don't even bother, right? Don't invest in the calculation. Go back to your design or whatever and change the parameters, change the construct so that to begin with, all of them are positive. So this is equally useful, although it doesn't give you asymptotic stability, but it enables you to exclude asymptotic stability a priori and see that there's something wrong and you don't even have a chance for asymptotic stability. Okay, so next time I want to do an example. I'm a bit over time, so I'll finish earlier. It's just a really nice classic example where these criteria were first used actually in the controls literature for a very real problem, which is the instability of steam engines, which was prevalent after they worked very well initially, the steam engines in the 1800s, but for some reason, instead of getting better, they became more unstable. And there was a puzzle to the math community. And somebody will discuss that, took a shot at that and actually use these criteria to explain and make design recommendations. Any questions? Sorry, I see a chat here. Did I mix up the stable and unstable eigenvalues, the direction of it? Quite possibly. Sorry, let me go back there. I tend to do that. So when I was drawing S1 and S2, I'm sure you are right. So S1 is minus 1, 1. So I would go, so that looks like, what did I mess up? So S1 is minus 1, 1. What I potentially messed up is S1 is not the one that corresponds to the stable one. Is that because that I didn't do the calculation, but you're right. I must have messed it up for the following reason: is that I know that the mechanical system, as I explained earlier, it should have this overall orientation of the trajectories. So I think I'm consistent with what I've written here, but I'm consistent with everything what I've written here, but what I've written here is wrong, right? So S1, which is minus 1, 1, that has to be the stable direction. So in other words, my apologies.
That's correct.
This is at S2. Thank you for pointing that out. And this is one thing I told you, I think earlier, that in a mechanical system, this can never happen. So, mea culpa. I would fail my own exam, right? So, I mean, you gotta then turn these arrows around, all of them. So this is the unstable direction. This is the stable direction. But then I'll work on this, okay? Because then it means that I have to relabel all these. Sorry about messing this up. At least I correct these. right? And then the labeling, and then I'm almost okay. So what do we have here? So for sure, this is the stable manifold. And underlying that, the stable subspace, the definitions are correct, but this is not correct. The stable subspace, I'll just say simply that this is ES, and the unstable subspace is EU, and the stable subspace is therefore here, and as opposed to what I've written here, this WS. Okay, and what else? This is the WU. Okay, and this would be then EU. And hopefully I'm okay now. Sorry about that. I should have noticed it. Actually, this is one of those consistency checks, but I wasn't paying attention. Indeed, it has to be the other way around. Thanks, and I'm sorry that I didn't notice the. Okay, so I think we're consistent now, right? Because, or did I mess things up again? No, I think this has to be right now, because this is what the pendulum phase portrait looks like. So -1, I think I'm correct now. Yeah. Oh boy. I said S1 and S2 are swapped around. So S1, so let's see, then S2 is the stable one. So then indeed, and this is then lambda2, and this is lambda1. Should be okay now, right? So lambda1 is the unstable one and corresponds to 1, 1. Yeah. So hopefully it's all consistent now. Sorry about that. Okay, any other remarks? Okay, we're done for today. Have a good rest of the week, and then we'll talk about this really great. I really find this example person very inspirational. So because there's a lot of physics and actual engineering reality in it, a lot of history too. So I'll do maybe a very little sort of just I'll write this out for the cubic case and then go for the example next time. So see you in almost a week, a little less than that. Enjoy the rest of the week. Bye.